Hi everyone, my name is Pugar and this is yet another academic ZNotesLive session on physics. And today, as usual, we have publisher Kaleem Akbar with us, and we will be going through refraction and total internal reflection part 2 today, which means we get to see more about total internal reflection, its applications, and we'll dive into past papers. This is applicable for GCSE and IGCSE students. Let's get started without further ado.
Hi, thank you again, Pugs. Thank you, ZNotes, for having me once more. Yes, guys, let's get in. We've got so much to cover today, and I really want you to understand this idea of total internal reflection, which I'm glad, that you've put at the front there, Pugs, refraction and total internal reflection, because a lot of people think total internal reflection is a separate topic from refraction. And although we're not doing it today, lenses is separate from refraction, dispersion is separate from refraction. It is not. All right, they're related, and you're going to see here we're going to deep dive. We're going to start with refraction and very quickly go into total internal reflection. So, guys, in front of you here, you're looking at two semicircular blocks. And Pugs, I've not forgot, I still editing this video. Making a video is the easiest thing to do. Editing the thing, I was going to swear there, it takes a lot longer. So that will be put onto this video or wherever ZNotes decide, guys, and they'll let you know. They'll let you know because the experiments are very helpful for you to visualize what's going on. So, guys, here is a semicircular block, okay? And that yellow line basically denotes that if you were to shine light along here, let me just draw on this. If you were to shine light right along there, that's when we're at the critical angle. Oh my God, those drawings, I really need to practice art lessons, anyone? But basically, that line is where the incident ray comes in and the refracted ray will run right along the surface of the glass. That's known, guys, as the critical angle of that material. All right. Now, here's the thing. If the angle of incidence, when I can find it, there we go. If the angle of incidence is less than that critical angle, right? So I want you to understand every material has its own critical angle. That's the bit to get. You don't need to know what they are, but they all have their own. If that green ray that I've got, so green light, comes in an angle smaller than that critical angle, so smaller than that yellow line that was there, I've now made red, then you will get what you've always got, refraction. All right, the light will refract. What does that mean? It changes direction when we went from a more dense medium to a less dense medium. In other words, in this particular example, from glass to air. Now, also remember, if I was to shine light, I'm going to do my best to make this straight. Let's give it a go. You know what? For me, that is an A star. When I go straight through the glass with a little squint, when I go straight through the glass, remember the ray of light doesn't change direction. Why? Because it's hitting both surfaces at 90 degrees. That's why the green light did not change direction here. Okay? Circles, if you've done this in math, you can go all the way around this circle and hit it at 90. You can draw tangents all the way around here. Whereas the flat surface, unless you're hitting it directly, you'll be hitting at an angle. Okay? So let me just rub this out. Eraser. Rub out my amazing straight line. Should have kept that. Okay. And let's crack on. Right. And in fact, you know what? I'll erase this too. So the only reason I drew this is if the light was shining right along that yellow marker there, you would have a ray of light going right along the surface. All right. And I'm going to explain the critical angle again shortly. But right now, we're sticking to normal refraction. What's normal refraction? If I go from less dense to more dense, I bend towards the normal. And in this example, when I go from more dense to less dense, I bend away from the normal. Now, what happens if the angle of incidence was greater than the critical angle? All right, so remember the yellow line is representing where you shine it for the critical angle. Now we get an effect called total internal reflection. TIR for short. Now, the angle of incidence, listen carefully, is equal to the angle of reflection. Whereas here, the angle of incidence is not equal to the angle of refraction. Guys, in the exam, you'll see R, R, R all over the place, but the R's don't always mean the same thing. Here, R would be refraction. And I'm just going to do lowercase to make our life easier here. Here, R would be reflection. Okay, I was just making the different incidence and incidence here. So incidence and refraction, incidence and reflection. I just made one of them capital to show you that there's a difference between them. Very often they don't do that in exams. Okay, they'll leave it the same. So, what's this all about? Very soon you're going to see some applications of total internal reflection. Very, very important applications in technology, guys. And they advance all the time. Fiber optic internet, endoscopes, burning tumors, etc., using fiber optics in your body to burn away a tumor. Fiber optics is used in communication, like I told you, internet. Fiber optics is used in decoration. Maybe you get these fancy lights that change color. They look like there's little stringy bits coming out of this plastic base. I've got a diagram shortly. In fact, let me just show you and you'll see what I mean, where you get different colors of lights, red, green, blue. You know, it's just decorative rather than for any other purpose. Now, I want you to remember again, there is a third scenario here. I'm going to do it one more time. If, and let's just actually make it yellow for good measure. If light came along here, then it will refract along the surface. That angle in there, let me give it a different color, would be known as the critical angle. Why do we call it the critical angle? You go 1 degree above this, you get total internal reflection. You go 1 degree below this, you get refraction. I hope that makes sense. Now, the bit that's not drawn here that I mentioned last lesson, I'm going to mention it again. Guys, very often, exam questions, they'll either show you the reflected ray all the time, or they won't. See right here? Let me just do it in green, since it's green we're using. There is a very, very weak, so I'm kind of doing it dashed, a very weak reflected ray. And the bigger I make that angle of incidence, that weak reflected ray gets stronger and stronger. And if I had the video ready today, I'm really sorry, you would have saw that yourself. You would have just thought, oh, look, there's this little ray, oh, and it's getting brighter and brighter and brighter, until such time you get total internal reflection. Think about what that means. None of the light's escaping. None of it. It's all staying inside the glass. I mean from this surface. I don't mean all the way down here. All right, that's just part of the experiment. But at that surface, it's staying within the glass. So, 2 conditions you must know for the exam for TIR. Condition number 1, it can only occur in the more dense medium. What the hell do I mean by that? Here, it can't happen in air. It can only happen in the glass. If it was water in air, it can only happen in the water. If it was glass and water, it can only happen in the glass. It has to be in the more dense medium. Condition number 2, the angle of incidence has to be greater than the critical angle for that material. Okay, I hope that makes sense. And the formula for critical angle, n equals 1 over sine c, or sine critical angle equals 1 divided by refractive index. Now, I don't want to make this too complicated. Those who really, really think about it might end up asking the question, we'll see. But this is really n equals sine I over sine r. I won't explain the complicated bit because it's IGCSE. But think about this. At the critical angle, the angle of refraction is 90. Sine of 90 is 1. That's where the 1 comes from. Okay? Now, those who would dig deeper would go something else, but I'm not going there. So if you're welcome to ask. I'm not trying to complicate it. This is the formula. I don't want to complicate it more than the IGCSE needs to. Neither do you. A-level students may go, oh, but wait a minute. Not going there. All right? N equals sine I over sine r. Here, sine of 90 is 1. Okay, uses of total internal reflection. I actually love this slide because there's some brilliant exam material right here that I am going to hit you guys up with right now. So, guys, these are called cat's eyes. And you know what? When I realized how these worked, I thought of myself, what an idiot as a teenager I was. I used to think, how cool are these lights that whenever daddy's driving the car, they know we're coming and they light up. And then when we go by, they go off again. How cool are those lights? Little did I realize that the way they worked, I was like 10, 11, 12, all right? But the way they work is the headlights from the car totally internally reflect from the reflector in cat's eyes. Cat's eyes is something you will find on a road, on a motorway, on an expressway. They can be red, they can be green, they can be orange, depending on your country. And it just shows you the lanes of the motorway. So I used to think they were so clever that they would light up, but they were only lighting up because the headlights from the car that you can see here are totally internally reflecting from the inside of the prism. Now, what kind of exam questions we can get here? This diagram here is exam question central. So let me go over it with you. Pugs, first of all, let's see if you want to help me here, Pugs. I'm just going to start making up letters. Can you tell me why the ray did not change direction at A?
Oh, because it's just coming straight. It's going along.
It's hitting the glass at 90 degrees, or it's going along the normal. If I was to draw a normal, guys, it would be right there. All right. Any ideas? Oops, my bad. Sorry, guys. I've kept my WhatsApp on, which was not a good idea. Let me just quit that. Okay, sorry. Right. Pugs, do you remember what happens to the speed of the light as it goes into the glass?
Well, the speed does
goes in.
Well, nothing happens. Nothing happens, right? Because it's just going straight.
Shall we fail Pugs today? Shall we fail them? Oh, is anybody watching? Shall we? No.
No, it does decrease because it does decrease because it's going into a denser medium.
Pugs, you're going into a denser medium. Now, where Pugs may have got confused, this happens to a lot of students. Sound would be the other way around. Sound speed would increase, lights decreases, and that causes a lot of confusion, right? Sound needs to vibrate. When sound goes into a solid, particles are closer together, more vibrations. I know that's not today's topic, but I'm just showing you where confusion can arise. So speed goes down. Pugs, what happens to wavelength?
Wavelength should decrease because your frequency should stay the same because we're looking at quote-unquote monochromatic light, which is to say same color.
So V equals F lambda, but listen, remember what Pugs just said, they're quote-unquote monochromatic. For you guys in the exam, say single wavelength or single frequency, even though what Pugs has said is layman's correct, but technically incorrect. Now, you might go, what the hell does that mean? Well, guys, to me, you and everybody else, weight's measured in kilograms. In the real world, right, the one we live in, even I don't go into a supermarket and go, can I have 50 newtons of apples, please? The person would look at me and think I want 50 kilograms, right? But it is measured in newtons. In the science world, it's measured in newtons. So here, monochromatic in the layman's world, okay, we would call it single color. But if you really delve into the physics, it's single wavelength or single frequency. It's a bit like the visible spectrum. You ask a student to go, oh, it's the colors of the rainbow. No, it's the visible spectrum. See, us scientists, we get pretty snooty about things. You just have to stick to it, okay? So, Pugs is absolutely right. Monochromatic, V equals F lambda. If V goes down, lambda must go down. But what we learn is that doesn't change. Why doesn't it change? Because it depends on the light source. So if you look at this car, it's given out a certain light source. It has a certain number of waves every single second. We won't go into the Doppler effect for anybody that's thinking that, right? Just it gives out the same frequency of light. So look at that. Already, I've managed to ask you a couple of exam questions. What happens to speed? What happens to wavelength? What happens to frequency? Why did it go straight through? Now, tell me. Let me just draw the normal properly. And no pressure, Pugs. If you can answer it, great. If not, I'll explain it. What do you call the effect at B? What do we call the effect at B?
That's just reflection.
Total.
Okay, no, wait. Total internal reflection.
Reflection. Total
Reflection.
internal reflection is
It's
staying inside the glass.
Yep.
Any ideas why it happens? I gave one.
Because it's greater than the critical angle.
The angle of incidence is greater. Look, guys, we've not even got to the second part of this glass thing yet, and I've asked like 4 or 5 questions, all examinable. So, yep, the reason why total internally reflects, the angle of incidence is greater than the critical angle, so total internal reflection occurs. Let me pick a different color. Green's kind of not doing it for me here. Let's be bright. So there's your angle of it. Oops, what did I do? That was silly of me. Give me a second. Angle of incidence, angle of reflection. Okay. Now, Pugs, what do you think would happen if the angle of incidence here was less than the critical angle at that point right there?
It would go out. It would go out of the medium, right?
It would. Some of the light, well done, Pugs. Some of the light guys would do what it's always done before, refract. Now, remember what I said to you. What that'll mean is the reflected ray inside here will be very weak. Sometimes they'll draw it, sometimes they don't. What I want you to do is be prepared for either eventuality. So if they don't draw it, I want you to have in your mind, yeah, but that happens. It's okay. They're not examining it. No big deal. And then when you see it, yeah, okay, they're going to examine it. Again, no big deal. I am prepared. I could ask you exam questions on this all day long, but I know that we've got some coming up, so I won't. And next, here is an example of a fiber optic, guys, glass cable that has total internal reflection. Okay, an endoscope, a device that the doctor can use to have a look down here. And I said it before, if you're really unlucky, somewhere else to have a look in the inside. I don't suppose it would be a pleasant experience. Hopefully you're asleep at the time. Right, total internal reflection means off the wall means the light can only come out at the end. So this is what I meant by decoration. I don't know if you've seen these guys, where at the end of it, it might turn green, it might turn blue, red as it's shown here, yellow, indigo. These are all colors of the visible spectrum. Here's an example of a fiber optic. And as you can see, total internal reflection occurs. Now, guys, I'm not going to go into core, cladding, all that kind of stuff. We're going to keep it nice and simple here. You've got a plastic thing on the outside to stop it from breaking. You've got your outer layer, fancy name depending on your syllabus, cladding, and you've got the inner core, but we don't need to make it that complicated. All you need to know is the only reason that effect is taking place is because the angle of incidence is greater than the critical angle for that material. Okay, that is it. If it wasn't, some of the light would escape, except here, the outer layer and the plastic sheath, the cladding, they're designed to make sure it really doesn't happen at all. But if it did, it would be less than critical angle. So moving on. Right, well, Pugs, unless you've got any questions now, I think I'll move on to the exam questions, or if any of your viewers have got questions. Nothing coming up?
Well, the only question that we had from a viewer was, are we going to do exam questions? So, yeah.
Yes, we are. Well, let's get into it then. May, June 2011, paper 3-1, guys. Figure 8.1 shows a section of an optical fiber. It consists of a fiber of denser transparent material coated with a layer of less dense transparent material. Core cladding, you don't need to even know it. One ray within the fiber has been started for you. State and explain, what happens to the ray already drawn after it reaches the boundary between the materials. Well, look, quite clearly, it's designed to do what? Totally internally reflect. In other words, keep all the information inside. Okay, this is how fast internet works. Look, you can write reflection but no refraction. Total internal reflection is what you want to do. This is just the examiner giving you a way of saying total internal reflection in a really long-winded way. Because some people, they'll see a bunch of lines in the exam, and they're like, Well, once upon a time, the ray did not go out and it stayed in, and it bounced off the other side and it stayed in. They basically mean total internal reflection. Okay? Where does this happen? When the angle of incidence is greater than the critical angle. Because look, guys, they wanted you to state. So for me, I would go total internal reflection. And they want to know why, because the angle of incidence is greater than the critical angle. That's the only reason. There are no other reasons. On figure 8.1, carefully continue the ray until it reaches the end of the optical fiber. Now, this is where things go wrong. I'll show you what a student does, then I'll delete it. They get to the end and they give it all this. Yeah, check this out, total internal. Woo, done. Right, there's a lot wrong with this other than the crap art, which I'm sure you wouldn't do. The biggest thing that's wrong with this, guys, is if you were to draw a normal right at the beginning. Okay, if you were to try to draw a normal at the beginning, look at that angle of incidence. It is huge. Look at that angle of reflection. It's tiny. So whilst you might be happy with most of your diagram if it was straighter drawn, okay, it's wrong because the initial angle was really big to start with. So when you get total internal reflection, what you must understand is, oops, move forward again, that the angle of incidence has to equal the angle of reflection. So what you've got to do in your mind is draw the normal straight down and then actually see what happens next. Look how big that angle is. But if you compare them, they are by eye the same, even over here. I'm not going to use a protractor. All the examiner's looking for is by eye, visually speaking, does it look the same? And you know what? See if you're like me, unlucky like me, and are garbage at art. This is what I would do in the exam. What am I doing there? Just with a little diagram, I'm saying, hey, examiner, I suck at art. You're not really. You're basically saying I equals R. You're telling them. So if you're even slightly miffed about you, because look, students will take protractors out for this. You don't have to. It's worth 1 mark normally, maybe 2 if you're lucky. But it's by eye. The examiner's going, yep, the student gets it. So if you really want to show you get it, just put in I equals R, and that'll be it. Game over. Done. So fiber optic cables are sometimes used to carry out internal examinations to the human stomach. Suggest one reason why the cable is made up of thousands of very thin fibers. Now, that's a hard one. A lot of students don't know this. But if you've ever looked at a rope, guys, like look very, very closely at a rope, it's as if it's got lots and lots of threads. If you ever look at it, even cotton, if you were to kind of pull it apart a bit, you know, like it frays. Like a lace, if you think about a lace, if your lace is the plastic bits ever came off, it frays at the edges. Why is it made up of so many fibers? All of them. Now, I know that we're talking about glass here, but the answer is exactly the same. It's easier to bend things like that. It's easier to stop it breaking. Look, forget the more detail or greater resolution. You need to be an A-level student to know that. Forget it. The bends easily and less likely to break is the thing that I would like to put across to you. Okay, the more you have, the easier it is to bend and less likely to break. You get one little glass fiber, much easier to break. Next, describe very briefly how the inside of the stomach is illuminated. Now, guys, if you're in a dark room, let's say it's nighttime, pugs, the electricity is shut down in your house. What's the first action you would probably take to allow yourself to see if the electricity's been shut off?
I would go looking for a torchlight, but I don't. I suppose that's what you were driving at.
Yeah. You either pull on your phone if it's still got battery and it's
Oh yeah.
on, or look for a flashlight. But here's the thing. See, when you put the flashlight on, how do you see? You can only see because the light is shining on the object
and it reflects back to you.
Light is coming back towards your eye. So what they're saying is briefly describe how the inside of a stomach is illuminated. Look, guys, your stomach is dark inside. So what they need to do is shine light down there in order for that light to be reflected back up to your eye. So how is it illuminated? Light travels down the fiber. You fire a light down the fiber. And then they say to you, Well, how do you see the light transferred from the detecting equipment to your body, the outside body? Well, reflected light's going to come back up. So if you're firing light down, just like Pug said about the torch, shine the torch in the room. Well, now your eyes can see whatever's being reflected. So the reflected light is now going into your eye. You are now able to see things inside the body. Now, I did have a picture of an ulcer. Pugs thought it was too gross and decided not to include it. So I had a picture of, if you looked inside this person's tummy, it looked like there was chewing gum stuck to his insides. Okay, the however you call it, my movie director thought it was too 18, it had to be like PG. So we removed it. It's all good. So describe briefly how the light from the stomach is transferred to the detecting equipment. Light comes back up. It's the same idea as a torch, guys. How do you see things? Light comes into your eye. Now listen, I hope you're not like some of my students, which I'll pick them up on and I'll laugh with them. There are some ray diagrams and students will draw light coming out the eye. Tonight, before you go to bed, turn the lights off and then tell me if you can see around the room. If you can't, there is no light coming out your freaking eye. Okay? You are not Cyclops from, I think it's Cyclops from the X-Men. All right? Light goes into our eyes, it does not come out of our eyes. Please be careful with that. People go, but what about cats? Cats have light. It's reflecting off the cat's eyes. That's why they're called cat's eyes. I'm talking about real cats now, not the diagram I gave you earlier. Okay. Here's a good refraction one to do, all right? Figure 7.1 shows a ray of monochromatic red light in air, incident on a glass block at an angle of incidence 50 degrees. State what is meant by monochromatic, like I told you, for the purposes of this, guys. Light of single wavelength frequency. Look what it says, ignore color, which is annoying because if you look at really old past papers, they accepted it, but not anymore. Somebody's taken umbrage to it at the exam board. For this red ray, the refractive index of the glass is 1.52. Calculate the angle of refraction. Well, now, guys, you've got the angle of incidence and you've got the refractive index. So what do? N equals sine I over sine R, or 1.52 equals 50 over sine R. Well, what am I going to do here? I'm going to rearrange. Sine R equals sine 50 over 1.52. Now, here's the thing I need you to watch. When you do sine 50 over 1.52, you're going to get a very small answer. In fact, let me do it. This is where a lot of students stop. So sine 50 divided by 1.52, and you get 0.5039. This is where a lot of students stop. That's sine R. You are not after sine R, you are after R. And the way you now do that is shift, sine, answer, and you'll get 30.26 degrees. I don't know why I just did that, it's right in front of me. 30.26 degrees, as is said on the slide. Okay, next. Here's an example of what we talked about last lesson, where they're just asking you without measuring angles. In other words, what I said to you last lesson, sketch it. Draw the approximate ray of the ray in the glass and emerging from the block. You're going from less dense to more dense. What does it do? Bends towards the normal. Here, you go from more dense to less dense. What does it do? Bends away from the normal. Notice this one and this one are parallel because they're both in air. They've got to be the same. Okay. The red ray in figure 7.1 is replaced by a ray of monochromatic violet light. Remember, single wavelength, single frequency. For this ray, the refractive index of glass is 1.54 and the speed of light in air is 3 times 10 to the 8. Calculate the speed of light in the glass block. Here's the other formula that I gave you, but we've done it shorthand here. Refractive index equals VA, in other words, speed of light in air, over VG, in other words, speed of light in glass, okay, which is equal to N equals 1.54 divided by, wait a minute. No. Guys, minor error. Let me just scribble this out. Ignore. All right. N is 1.54 itself. So what you want to do is, I think that VG shouldn't be there. So Vg equals 3 times 10 to the 8, because that is going to be the speed of light in air,
Speed of light.
divided by n, which is 1.54. So actually it was fine, it's just that little bit added on at the end. And what you'll get is 1.948 times 10 to the 8 meters per second. Now listen, a lot of students get hung up on standard form. You do not need to use standard form. You can do 1948, 48, 11111612, blah, 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 blah. You can do all of that. In school, your teacher won't accept it. I wouldn't accept it because we're trying to teach good habits. But I'll tell you what, the exam board will. 100% the exam board will. Okay, they're not testing your math, they're testing your physics. So, erase it. Okay. Use a ruler to draw the approximate path of this violet ray in the glass block and emerging from the block. Make sure this path is separated from the path drawn in the red line. And this is where I was hoping that the video would be ready. So I'm really my bad. Because what you'll learn when you look at the video is, and we didn't do dispersion, but if you ever do dispersion, it's red, orange, yellow, green, blue, indigo, violet. So what does that tell you? Well, if you look at that experiment, red bends the least, violet bends the most. So what's going to happen here? The exact same thing as you can see, except it will refract even more at the beginning. Why? Because it bends even more. So it's the exact same idea, bend towards the normal, bending away. It's just that it does it more. Violet rays do it more because you've got red, orange, yellow, green, blue, indigo, and violet.
Just one, probably an easier way to think of it in terms of thinking of dispersion, or like if you're having trouble with this concept, is just think of the rainbow and just say that with GR mnemonic, right? So you go from violet to red, so you know that red disperses the most violet rays. So yeah, you could try that as well. Yes.
Go for it. Yeah, absolutely. Red would bend the least in that example, and violet would bend the most. Absolutely, guys. Thank you, Pugs. It's always good to hear different ways of thinking about it. So I appreciate that. Thank you very much.
Sure.
Right, guys. So here's the last question for today. And look, oh, have we just done this? What is the term monochromatic? This is what I see, exam practice. The more you practice, October, November 2011, paper 3-3, you'll just see the same thing over and over again in a different way. I was doing a lesson this morning, and we're doing what we did with you guys, specific e-capacity, a few weeks ago. We did 5 questions in the trot, and like 3 parts of it was like, you're just like same. Slightly different words, but meant the same thing. So what's meant by monochromatic? Single wavelength, single frequency, single color. Ignore single color, okay? Ignore chromatic, which I don't get because technically it's that whole kilograms Newton thing. But anyway, we'll leave them to it. Use the information to determine the refractive index. Now we need to go back for this. What's the angle of incidence? 45. What's the angle of refraction? 26. So what we do over here, n equals sine I over sine r, sine 45 over sine 26, we get refractive index 1.613. The angle alpha at 9.1 is not drawn with the correct value. State the correct value. Let's go back here. Well, guys, if that is 45, quite clearly we can see that this is exactly the same. Again, I apologize for the really junk art. Let me just erase that one. So we can see the 2 red bits are the same. So what do you think the angle is, Pugs?
Okay, so would it be 90 minus 45? No, I'm getting it wrong.
Well, no.
Or would it just be 45?
Yeah, it's just 45. 90 minus 45 would have given you 45.
Oh, yeah, same thing. Yeah.
They're just the same thing. They are just the same thing. But here's the thing, guys. That is the angle of incidence. That is an angle of refraction, but they are not related to each other. That was a really dramatic cross. Now let me delete all of that and show you what I mean. Okay, bit of drama there. Right, let me go back. Guys, what I mean is this I goes with this R. Okay, and this I goes with this R. That I and that R are not, don't confuse them. And one of the mechanisms I gave you not to confuse them, they cannot be the same. So don't confuse them. you treat each boundary on its own. Air to glass, glass to air. So please do not confuse them. So we've got the angle, 45 degrees. Next, after the ray has left the glass block, it passes into a block of ice whose refractive index is 1.31. How does the speed of light in ice compare with the speed of light in air? Well, if you think about it, glass was like 1 point whatever we got there. What did we get? Let me just remind myself. It was 1.6. Air is going to be less than that because it's less dense. So the speed of light in ice compared with air, well, the speed of light in, how does the speed of light in ice compare with, so the one in the ice is going to be slower than the air, or air is going to be faster. You can do it both ways. So ice is slower than air, or air is faster than ice. You can answer it both ways. What about the speed of light in, how does the speed of light in air compare with the speed of light in air? I'm sure that's supposed to say the speed of light in air with the speed of light in, not
Yeah.
really. Guys, we'll fix it. I'm sure it's supposed to say speed of light in air with speed of light in, well, let's just find out. I'll work it back.
Yeah.
So they mean, how does the speed of light in ice compare with air? Definitely slower. How does this, that's supposed to say glass. How does the speed of light in ice compare with the speed of light in glass? The speed of light in the ice is going to be faster. Why? Because it has a lower refractive index. So sorry about that, people. Speed of light in air, ice with air, ice is slower. Ice with glass, ice is faster. And it's all to do with refractive indexes. Guys, I hope that makes sense. Pugs, I know there's like another, we could keep going on and on and on, but I don't know how you feel with where we're at.
Well, if we've got time, I think we can go for one more question if we've got some.
Yeah, right, okay, guys. Figure 4.1 and 4.2 shows a semicircular block as rays of blue light are directed into the block at different angles. The rays are directed towards the center of the block and no refraction occurs as it enters the block. Well, we know why it doesn't refract here because it's hitting along the normal. At the angle in figure 4.1, no refracted ray emerges from the block. So what is the critical angle? Well, what you need to do is you need to draw yourself a normal. In fact, I'm sure there was one already drawn if I never bothered doing this. So let me just erase. So the angle of reflection is 50 degrees. Now let me just show you that normal. So there's the normal right there. Why is it the angle of the critical angle is 50? Because if that's 40, all of this is 90. So the critical angle itself is 50, which means that's also 50. Okay, it's just simple. Sorry, let me rephrase that because we don't know it's a critical angle. My bad. My bad. Totally my bad. Can't be the critical angle because I don't see anything along here. So that's rubbish. Let me just rewind. I misread the question. All thereafter is the angle of reflection. If that's 40, then 90 minus 40 is 50. So if this is 50, so is that. So the angle of reflection is 50. Then it says, what kind of reflection is occurring at the point C? Well, guys, it's total internal reflection. Okay, it didn't ask us why, it just asks what's happening. Next, the experiment in B is now repeated with red light. On figure 4.3, draw and label the paths of the reflected and refracted rays of red light. The dashed lines show the path taken by the blue light. So very similar to what we just did. Very similar. So what happens here? The angle of reflection will be exactly the same, but because red light has a smaller refractive index, it will refract instead of reflect. The blue light will reflect. Remember, if you think about it, Roy Gibiv, as Pugs was saying, red, orange, yellow, green, blue, indigo, violet. Well, if blue is reflecting, then red bends a lot less, so it's likely to be refracting. And if you had a normal right here, it would be bending away from the normal. I hope that makes sense. And then next, Figure 4.4 shows a 45-45-90 prism used in optical instruments. Part of the path of the ray light passing through the instrument is also shown. Light leaves the instrument along B. Now, this does take a lot of, getting used to for students. What you need to do is take that prism and draw it in reverse. Why? Well, look, guys, notice it went straight through here and straight through here. So I needed to go straight through somewhere here and here in order for it to come out at B. And the key is it's totally internally reflecting at the flat face right there. So we need the flat face this way so that it does the exact same thing. I hope that makes sense. So you basically take the triangle and you flip it. Right. For myself, Pugs, unfortunately, that's all I've got time for today.
Sure thing. Let's call it a wrap for today. Thank you, Kaleem, for walking us through total impedance reflection and also spending time on the past paper. And once again, we'll be back on Tuesday with more sessions. For updates, follow us on Instagram, and you can subscribe to the YouTube channel. All the resources for this session, by the way, are in the description below, so do check it out. And we'll be adding Kaleem's practical videos in the coming weeks as well, so that some more exciting live demonstrations around the way as well. All right. See you guys next Tuesday. Bye-bye.